Hello, welcome to a video on some topics selected from Geometry of Numbers. It's a textbook written by C.D. Owls. The ninth chapter of the text is New Principles in the Geometry of Numbers. In this chapter we can see the Theorem 9.1. It's very famous as Brushfield's theorem, and the Theorem 9.3 will also be discussed here. For giving the proof of the Theorem 9.1, we need a lemma. The lemma is given the number lemma 9.1 in the chapter. So first we can see the statement of the theorem, Brushfield's theorem. The statement is if the area A of a two-dimensional set C is greater than the integer n, and then by a parallel displacement of C, by a parallel displacement of the set C that can be made to cover at least n plus 1 lattice points of gamma. Here what does it mean, the theorem? If you consider the set C on the plane on R2 having minimum area given by the integer n, it must be greater than, minimum area means the area of the set must be greater than or equal to n. Sorry, it must be greater than n, must be some number greater than n. Then that set can be displaced, it can be moved along the either in the parallelly or horizontally, either vertically or horizontally, parallel to x and y, x or y axis, or and both, parallel to both axis. We can obtain a new position in which that new position, you can see that the new position of C contains at least n plus 1 lattice points. It contains at least n plus 1 lattice points of gamma. We need some preliminary ideas on this, on the set, to discuss to understand the proof of the result. Here see, the set can there is no strict restrictions on the set in the case of previous results. There we took only the symmetric sets with the center of symmetry at the origin, and must be convex, and those restrictions were there in the previous cases. But here we are free to take any set C which may not be asymmetric about a central point. But one thing is important, we can divide the set, we must be able to divide that. We can divide that set C into subsets C1, C2, etc., to Ck into K subsets. But this number K doesn't come arbitrarily. It depends on the size and area of the shape of the given set. And we can also define some rectangles corresponding to these subsets, so that we can understand more referring this figure. Consider this example 1. In this figure the set C is given. The set C is given, and you can see that that set is divided into subsets, but it is not an ordinary division of the set C into subsets, and these subsets are given names C1, C2, C3, etc. up to C1, C2, C3, C4, C5 and C6, C7 and C8. All these are the names given to the subsets. Thus there are 8 subsets of the set C. Also you can see that there is no intersection. Any two of these subsets you take, there is no intersection, and their union is the whole set. We can also see that the union is the whole set. So it's a kind of partition of the set C. And corresponding to the set C, you can see the C1, the subset C1 is present in the rectangle. You can take rectangles on the plane and see the rectangle R1 contains the set C1 completely. So that rectangle is given the name R1, and the rectangle R2 contains C2, so R2 is chosen its name, and this rectangle contains C3, so R3 is the name given to that rectangle. In a similar way, we can see that each subset belong to exactly one rectangle, and that rectangle is named accordingly, according to or matching with the they are named matching so that it matches with the names of the subset. Okay, after completing this, you can we can now transfer. We can take all these rectangles along with the subsets to a single rectangle, which is at a distance from the original set C. So here we take that rectangle. The rectangle R will be single. The name R will be used to name that rectangle, and we then place these. We place these rectangles one by one on the rectangle R. So as we place R1 on R, we get that region. We get the subset portion also there on R, and so C1 is there. C1 hence C1 is marked there, and as we place R2 on R, then we get C2, the corresponding C2, the subset C2 portion there. In a similar way, we get all subsets C1, C2, C3, etc. to or up to C8 can be obtained at the in the same region, capital R, in the same rectangular region, capital R. So we get divisions of so all 8 curves will be there, but here only you can see only 2 curves, because as an example, to get clarity to the figure, I have transferred only 2 rectangles to 2 rectangles along with the subsets to that region R. But here you can see 2 more R4 and R5 are transferred to another rectangle, but in our actual proof, it may not be transferred to different rectangles. It must be transferred to one and only one rectangle, which is named R. I mean, all subsets must come as part of the single rectangle R. Okay. This is very important for discussing the next lemma. Okay, we have that lemma which states that an interesting thing now we can understand, which comes as the statement of that lemma. Lemma 9.1 says that the square R contains at least one point x. See, the square R contains at least one point x that is covered by at least one point x that is covered by the parts by the subsets or parts that is covered by the parts or subsets C1, C2, etc. to Ck no fewer than n plus 1 times. No fewer than n plus 1 times. That is important. No fewer than n plus 1 times. That means if we assume that all points of R are covered by the subsets of C1, C2 and Ck at most n, if we assume that it's a complementary portion of the statement of the theorem. It's the remaining part of the statement of the theorem, or it's the complement. So we want to prove, to prove the lemma, we are going to adopt the technique that we just assume that the complement is true. then we proceed further to obtain a contradiction. So we assume that the complement portion is true, the rest of the portion of the statement is true, then we try to get a contradiction. Okay. For that we suppose that, so coming to the proof of the lemma, we suppose that when the sets R1, R2, R3 etc. to Rk, R1, R2, R3 etc. to Rk are piled on a square R, this is the same thing that we discussed. Every point of R get intersection with only less than or equal to intersection with, or at the most n points, sorry, n subsets. Point of R get intersection with only less than or equal to n sets, n subsets C1, C2, n of the subsets C1, C2 etc. to Ck. So then what we are going to do, we take back these sets to its original position in C, and then we get that the area, then we get that the area of C is then at most n. As a result, what happens is the area of C then becomes at most n. It cannot be area of C cannot cross the number n, and thus we get the contradiction, that because contradiction to the fact that the area of C is greater than n. That is the assumption, that is the fact that we have accepted in the beginning of the or in the statement of the theorem. We have accepted that in the statement of the theorem we have accepted that the area of C is greater than n. So actually now the statement obtained here in the lemma, as a result of our assumption that we have taken in the beginning part of the lemma, we have obtained a contradiction. So we have to remove that contradiction. We have to get we have to escape from the contradiction. So for that we have to correct that there exists at least one point, say we can call that point x in R, which is such that which is covered by the subset C1, C2 etc. to Ck no fewer than n plus 1 times. Hence we complete the lemma part, proof of the lemma. So we okay. Next what we do, and we then poke a needle straight down. So we now we take, since we have one such a point, and we take that point, say x, and at that point we poke a needle, and this procedure makes a hole in that at that point it makes hole, you know, but that point belongs to minimum at least n plus 1 subsets. So this hole will be made at each and every subset, at a point of each and every subset of a C. So then what we do then, and we then take back these subsets we take back all the subsets to its original position as part of now it becomes part of the original set of C. And then you can get n plus 1. How many holes will be there? You will get n plus 1 holes due to this n plus 1 intersecting sections. Due to the n plus 1 intersecting sections, you will get n plus 1 holes in the original set C. So for illustrating this, you can refer this figure, this example number 2. Here we have taken for convenience we have taken a symbol set. That symbol set has this L shape, this big L shape, and this set has this set C. It shares C1 with R1 and C2 with R2, C3 with R3, C4 with R4, and C5 with R5. The rectangles. So there are 5 rectangles, and then we take them one by one to these rectangles are taken one by one and pile on a separate region R, and that makes some points intersection, some points of that makes the points of the region R having intersections with the subsets. See, all the points belonging to this 1/4. We can here in this situation we can divide the region R into four sections, into four small rectangles, and the first small rectangle, gets or has intersection with the subset of C4. So all the points belonging to the first rectangle, small rectangle, first 1/4 of the original rectangle R has intersection with the subset C, and the second small rectangle has intersection with C3, and here this portion has intersection with two subsets C2, C3 and C4. This portion has intersection with 1, 3 and 5. At this moment you may remember that the area of what is the area, you can see the area of the set C taken in this case. In this example we have taken the set C, and you can see roughly you can calculate the area. See, and this much portion you can transfer the okay. See, and you can take this portion and you can place it here, and there you get okay. If you place this 1/4 portion here, it's an empty portion, then you can complete this portion. So 1 unit here, and then we have already half unit here, but half unit here. You can place these two 1/4 rectangles one by one here, and over that here you can place, and thus you get that area of the given set C is 2 in this case, 2 units in this case. So since 2 units are the area, 2 is the area of the given set here, the value of n in this case is 2. N is equal to 2 in this case. So after seeing that n equal to 2, as per the according to that the statement of the theorem, then how many, according to the lemma, how many intersections must be there? Maximum intersection. Coming to that intersection part, there must be there must exist in the region R. In R there must exist at least one point having n plus 1, since n in this case is 2, n equal to 2, then 2 plus n plus 1 equal to 2 plus 1 equal to 3. So at least 3 sets must be, and there must exist at least one point having 3 intersections, having intersections with 3 of the subsets. So there must exist at least one point having intersection with at least 3 of the subsets. These 3 comes from the number n plus 1, where n equal to 2. But here actually you can see that there exist infinitely many such points, because all points belong to the 1/4 of this region, 1/4 of the original region R has the property, because they have intersections with the sets of C2, C3 and C4. But all those belonging to this region also has the same property, but they have intersections with the C3, C1 and C5. But we are not interested in, we don't want actually all of these points, we want only one point, exactly one point. And then after selecting one point, you have to poke a needle at that selected point. So here we take that point, we select a point. In this case we select a corner point here, and at that point we poke a needle, and this makes holes there, and then we translate back the corresponding sets to its original position. Then you can see that it makes impressions, or it makes holes in the original set C. due to the hole here which belong to the part of which belongs to the part of C5. When C5 is transferred to this position, C5 is transferred to here, so we get that hole here. But when C3 when it is a part of when the needle hole is a part of C3 is this L-shaped set, and you get that needle hole at this position, a needle hole here. Similarly, due to the set C1 you get the needle hole here. Yeah, here C1, this is C1. So as we have made a hole here, and you will get a needle hole here. Thus we have now we have three different places, three different points where we have needle holes in the original set C. Similarly, but if you consider a different situation, a different point, considering this different region, and suppose you make a needle hole here, and when it is transferred back, then you get the similar the holes you are going to get in the second case. Due to the second case, you are going to get at the same prices that you can check, and you can verify it. Okay. And this is the main part of the theorem. And what do we do then? Thus we have n+1 holes, and then by slightly adjusting this original set C. After that, after obtaining these n+1 holes on C, then we make some adjustment. We are adjusting that set C. We can adjust the set C so that we can completely get the 3 points inside. We get the 3 points inside inside the set C, inside the new position of the set C. We can slightly adjust in the downward direction, vertically downwards, or we can slightly adjust in the horizontal direction, either to left or to right, or vertically downwards or upwards. You can adjust to, because here you can see the 2 points obtained are on the boundary, so you can get them well inside the set C, in the new set, in the new position of the set C, by this adjustment. Okay, coming back to we can now see that these lattice points are marked by pinholes here. In our example, there are 3 points, and those 3 points are lattice points because we have chosen the points in such a way that we get easily the lattice points. But on the other hand, if you are taking the point here in order to poke the needle, suppose you are selecting a point inside it, the steps will require much a little more some more additional description, but since this is not the case in the proof given in our text, so we don't go to that additional description. Here we get that means we have selected the points in such a way that we get easily the lattice points which are at the corner of the subsets. So using these lattice points, and thus we can see that the 3 lattice points are marked by the pinholes, and by slightly moving the set C downwards, and it is due to the presence of some of the lattice points on its boundary. You can slightly adjust C downwards, then we can completely get the 3 lattice points inside the set C. In general, by moving C either vertically or horizontally, or both, or conveniently in some cases in both direction, we can get n+1 lattice points inside the set C. Okay, so this completes the proof of the theorem 9.1. Now we come to the next theorem. Next theorem is theorem 9.3. The statement is that let C be a bounded subset of R2, or bounded set of points in R2 whose area exceeds 1. Let C be a bounded set in R2 whose area exceeds 1. It is greater than 1, and then there exists at least 2 points P1 x1 y1 and P2 x2 y2. There exists at least 2 points P1 x1 y1 and P2 x2 y2 in C, such that the difference point we make this is a new point. The difference point, we make that difference, we can make the difference point by giving we give the name P. The difference point is made by subtracting the x coordinates and one of the x coordinate from the other, and by subtracting one of the y coordinate from the other, and we get that, and we write as a point. Then we get the difference point. The difference point P is x1 minus x2 and y1 minus y2. It has integral coordinates. The important thing is that we get the difference point. Always we can make a difference point, but here the important point is that the difference point has integer coordinates. See, the difference points has integer, but in the points x1 and y1, the values x1 y1 and x2 y2 may not have integer coordinates or integer values at all. Even though they may not have, these coordinates don't have integer values, we are going to get integer values here, and that is the main important interesting thing regarding this difference point. How do we get this? And we can see it from the lines of the proof. Okay, proof is let's start the proof. Since the area of the since it is given that the area of the set C is greater than 1, the area of C is greater than 1, we are now in a position to apply the Birch-Fields theorem, the previous theorem. We can apply the Birch-Fields theorem. Now the general form of Birch-Fields theorem, the general form of Birch-Fields theorem is that I can give the statement of the general form of Birch-Fields theorem. General form of the Birch-Fields theorem, which states that that theorem is given as theorem number 9.2. The theorem states that a bounded set of C, a bounded set of points C with an area A can be translated on gamma so as to cover a number of lattice points greater than A. A bounded set of points named C having area A can be translated on gamma so as to cover a number of lattice points greater than A, so that it can cover the number of lattice points greater than A. So this is the general form of the Birch-Fields theorem. Then comparing it with the general form, here the set C is there. C is same. We have a set C. It's bounded. It is given that it is bounded. So we have a bounded set C. But what is its area? Where there in the general form, area is given as E equal to A. But in this case, in our case, in the current situation, the area of the set is equal to 1. But in the general case, if the area is equal to 1, then it can cover greater than A lattice points. Greater than A lattice points means at least greater than A lattice points. We mean that the integer part. You take the integer part of A plus 1 lattice points. It can cover at least the integer part of A plus 1 lattice points. But in this situation, the current case, we have the integer part of the area equal to 1, and plus 1 gives us the number 2. So using the Birch-Fields theorem, applying the Birch-Fields theorem, we get that C can be translated on R so as to cover at least 2 lattice points. So C can be translated to a new position, and that new position will be labeled C dash. There will be no change in the shape and the size of the set C. without changing the shape and size of C, we are just translating that C on R2, and then you can get a new position C dash such that it contains at least 2 lattice points. How do we get this? Applying the Birchfield's theorem, the general form of Birchfield's theorem. Okay, now we can take this lattice, thus now we have a new position for C, that is C dash, the new position C dash, and we have 2 lattice points which are in C dash. On C dash, corresponding to C dash, we have 2 lattice points. Let's refer the figure now. Okay, this is the given set C. Take this green. This blue, the blue set, blue bounded the set bounded with the blue curve, closed curve is the given set, and that blue colored set is then translated to the red colored set. It is translated to red colored set, and applying the Birchfield's theorem, it is translated, and then in this translation you get 2 points. So in the beginning there is no idea about the points P1 and P2. So we are blind about that. There does not exist any point. We don't say anything about the existence of P1 and P2. Those points come only in the final stage of the proof. So here, how do we start? We are given with we are given a set C. That set C is taken here, and that set is then translated to a new position. So this red colored position is red colored set is a C dash. So this is C dash, and in this C dash, applying because since the area of since the area is same, area of this new set is the same as the area of the given set. So its area is 1, and then applying Birchfield's theorem, we get or you can find 2 lattice points. Exactly, they are lattice points. They are accurately they are lattice points. So 2 lattice points are there present, maybe on the boundary. Okay, and these lattice points are given names P1 dash and P2 dash, because its name is C dash. The new set is C dash. So C prime, we name them P1 P1 prime and P2 prime. We give the name P1 prime and P2 prime. And then it's very clear that as they are lattice points, the coordinates of P1 prime and P2 prime are clearly integers. Coordinates of coordinates of P1 prime and P2 prime are clearly integers. Now you can join this vertically. You can draw a vertical line from P1 prime and a horizontal line from P2 prime. By joining them, we can draw a vertical line passing through P1 prime and a horizontal line passing through P2 prime. Of course, they will intersect at a point, and that point is P prime. The point of intersection of these 2 lines is P prime. Now it is clear that the distance between P prime and P1 prime, distance between P prime and P1 prime is the difference of the y coordinates of P1 prime and P2 prime. See, once again, that difference, the difference between, or the straight distance between P prime and P1 prime, or the distance between the points P1 prime and P prime is the difference is equal to the magnitude of it's equal to the magnitude of the y coordinates of the lattice points. Difference between the y coordinates of the lattice points. Similarly, you consider the distance between P prime and P2 prime. Then here that distance is the difference between the x coordinate, the magnitude of the difference between the x coordinates of the points P prime and the points P1 prime and P2 prime. X coordinates of the points P1 prime and P2 prime. It is the difference between the x coordinates of the points. Okay, then after thinking about that, okay, after developing an idea about these differences, after developing this idea about the differences, we can now think about translating back the set C dash to its original position. Original position is C. Now we translate back the set C dash. We translate back the set C dash to its original position, and along with this what happens, naturally the points P1 dash, P1 prime and P2 prime will also get translated to the original set C. Once again, P1 prime and P2 prime will also be translated to its original to some point. These 2 points will be translated to its corresponding points. That is correct. P1 prime and P2 prime will get translated to the corresponding points. Those points are here in the new set. In the original set, they are named P1 and P2. So the points are translated to the points P1 and P2 in the original set, and hence this point, the point of intersection, will also get translated to a new point of intersection P. So all these translations are quite natural, and there is no doubt, and they will happen. After that, you can see that there will not be any change when we compare the distances of when we compare the distance between P prime, P1 prime, and P and P1. We compare the distance between P1 and P prime and P1 prime, and they are same. Similarly, the distance between P prime and P2 prime, the distance between P prime and P2 prime, and the distance between P and P2 are same. So the idea behind it is very clear, very simple, and very simple lower class geometry is there. So we can accept that, and since due to that equality, you can write it, that is the distance between or the magnitude of P1 equal to magnitude of P1 prime, P prime and P1 prime equal to but the question of but we have two values x1 and x2. Now one more thing I have to mention here, and P1 and P2 are the corresponding points of P1 prime and P2 prime in the new set, in the original set. P1 and P2 are in the original set, corresponding points of P1 prime and P2 prime. But we consider that, or we think that their coordinates are x1 y1 and x2 y2. That is the point. We assume that the P1 has the coordinates x1 y1 and P2 has the coordinates x2 y2. Now you can write this expression, assuming that the coordinates of P1 is x1 y1 and the coordinates of P2 is x2 y2, and then comparing the distances as I have described. I have just described, then you get that modulus of P1 equal to modulus of P dash P1 dash equal to the modulus of x1 minus x2. But clearly it is an integer because you get that this distance is an integer here. It's because the coordinates of in the referring that C dash and the nature of the points P1 dash and P2 dash, because the points P1 prime and P2 prime are lattice points, so their coordinates are all integers, and we get that. As a result, we get that the distance is always expressed in as the difference of the coordinates. In this case, here this distance is expressed as the difference of y coordinates. That's an integer. Also here the distance which is parallel to the x-axis is expressed as the difference of y coordinates. But both y coordinates are integers, so we get that difference is an integer. Difference an integer number, so we get its modulus is also an integer. Since the same differences are here used, since these differences are compared to the differences here, and it is seen that they are same, so we are going to get that the difference when they are expressed as the difference of coordinates in the new in the original set C, and in terms of P1 and P2 we get that modulus of x1 and the x1 minus x2 an integer, and modulus of y modulus of x1 minus x2, or the other way also you can write modulus of y2 minus y1 is also an integer. Thus both of these quantities are integers. Hence, what is the conclusion? What is the point where what is the point that we can conclude? We can now at this point at this moment we can conclude that we have obtained 2 points x1 and x2. Now here we have in the final stage, in the last stage we have obtained 2 points P1 and P2, but those points correspond to P1 prime and P2 prime, but they have the coordinates x1 y1 and x2 y2. x1 y1 and x2 y2 are the coordinates, but the difference when we take the difference of the coordinates as x2 minus x1, we get that's an integer, and when we take the difference of y2 coordinate y coordinate, when we take the difference of y coordinate, that also is an integer. Hence we can conclude that the set in the original set C contains 2 points, or there exists 2 points P1 and P2 in the original set, such that when we take take the difference of its x coordinates and the y coordinates, once again when we take the difference of x coordinates and y coordinates, we can see that those differences are integers. Okay, thus once again finally we can say that there exists 2 points given a set C, given a non-empty set C having area greater than having area 1, given a set C having area greater than or equal to 1, then we can say that there exists 2 points, at least 2 points in C, such that they are difference point. Actually these values belong to, when we take these values and when we compare it with this difference point, the difference, this is the point, difference point P, x1 minus x2 y2 minus x1 minus x2 y1 minus y2, and such that we get that when we take the difference of the coordinate values, those values, there are 2 values and those 2 values are integers, so we are going to get in the first position an integer, and second position also we get an integer. Thus the difference point is an integer, gets integer coordinates, or the difference point is it's an integer point. Okay, that's the end of the proof of the theorem 9.3. Okay, okay, thank you.